Been a while since you've seen this, I imagine. So I'm about to call them again. We tested it. Hey guys, don't worry about the video recording. Don't worry about the video recording. I'm recording this. My view is better. And my view also includes, cut the sensor, you can take a look. So this is the live stream.
This camera?
Yeah. We're just waiting on Chris. Okay, there's Chris. Hello, hello.
Hello.
Okay, can you hear us?
Yeah, loud and clear.
Okay, you should be able to now see the live stream. So the combination
I
view.
can see the slides.
Yeah, so I've got two views. One like this and then one with it flipped. So like this. Can you see everything, Chris?
I can see the slides.
Yep, great. You can't see the slides, or you can?
I can.
Okay, so then we're good to go. Okay, for those of us joining live via Facebook, feel free to ask some questions if you choose to, but keep in mind that I will only be able to answer these after the live stream. Okay, now maybe I should be a little nervous.
Okay, so it's time to start public witness by Damian Constantine.
Constantine.
Okay, so this is just a 60 minutes, 14 minutes presentation, and 20 minutes Q&A. Please start.
All right. Well, hopefully you've had a good day. If you don't know me, my name is Damien. I'm going to be presenting about my PhD thesis, which is entitled Towards Large-Scale, High-Fidelity, Collaborative Augmented Reality Experiences. So, just before I begin, a quick overview. I'm going to be first talking about the vision of my intended PhD project, what drives it, creating such a system for large-scale, high-fidelity, collaborative augmented reality, and evaluating IAR. Then I'm going to just wrap it all up and provide some conclusions. And as you can see on the slides, this is linked to the relevant chapters on my thesis. So, before I begin, let me just explain what the vision of my project is. The aim of my project is to be able to deploy a large-scale, high-quality augmented reality video game which involves many users spread out amongst campus-sized areas. Now we're talking university-sized areas, more specifically the NICE campus. And the idea is that people in the distance, like the guy up in the building, can look into the people below and interact with the content below. So before I continue, I need to define what fidelity requirements are so that we can keep up with the rest of this presentation. So for the first part, I look at what's virtual real interactions. So for example, if we have a virtual ball, does it bounce off a physical real world wall? Or accurate registration. Now this is related to the virtual content that's displayed. So for example, if we have a statue bust, is it placed correctly on the stand in front of us? We also look at spatial temporal consistency, and this is meaning when the interactions occur, are they occurring at the correct time and at the correct place for all users? Then finally, in the second part, I look more into the visual consistency of the AR scene. So that means that the computer graphics content rendered to us displays the same depth of field, same shading, and same lighting properties as the real-world objects. Moving on, as I said, I'm going to talk about this in two parts. The first, designing and creating a large-scale, high-fidelity, collaborative augmented reality experience, and then evaluating a subset of the elements in the experience. Then, in the second part, it's an extension of my master thesis work, which evaluates a system that creates refocusable computer graphics content using an optical see-through head display setup. The contributions of my PhD thesis are as follows. First, this work is the first to explore the large-scale, high-fidelity, collaborative augmented reality domain. Second, this work establishes a design space and guidelines for the same domain. Third, this system improves the accuracy of synchronous poses between multiple SLAM systems. Fourth, I create the first instance of a LSHF car experience. Fifth, I show that for virtual repellers, in such an experience, they work as effective crowd control elements. Then, finally, in the last evaluation, I show that for optical see-through AR, rendering computer graphics based on the measurements of the user's eye improves the overall fidelity. So now we can actually get into the guts of this presentation. To start with, I'm going to go over the first part. So, of course, everybody knows Pokemon Go. It was one of the first AR experiences brought to the end user, and everybody thought that this would make AR great. However, as you can already see in the video, there's many problems with the AR experience. There's visual content jitter, content appears in front of walls when it shouldn't, and it doesn't look nice overall. And for this isn't what we imagine true AR to be. We can think of an AR experience by two parts. The first is the fidelity or the quality of the experience. And for this we have low and high fidelity. Low being, does content accurately register to the right place? Are there visual occlusions? Is there virtual real interactions? And we can also classify them by the scale. And for this we're discussing simply room scale versus city, campus, global scales. This allows me to essentially categorize my related work. So typically, in most AR instances, especially if you look on the relevant Play stores for your mobile devices, you would normally find these very handmade collaborative AR experiences that are not so high quality and not so high in the scale either. However, more recently in research, there's been many things that have been shown, for example, AR Quake, which is capable of large-scale interactions, but uses sensor-based tracking and therefore isn't capable of the high fidelity that we need. Alternatively, we have things like the HoloLens and the Magic Leap that are more than capable of showing us some of these high-quality interactions. However, all of these experiences are still limited to the room-scale environment. So this is where my work comes in. I intend to be the first to explore the large-scale, high-fidelity domain. Then you're wondering, why hasn't this been done yet? So this is actually because of two reasons. The first part of it being the technical, and the last part of it being the user interface and design. So let's talk about the technical first. Imagine a typical AR scenario. We have a person with a head-mounted display or AR device in an office space. We can of course obtain the pose of a user and the map for that surrounding area. However, if we added a second person in a second space, then the first person inside wants to interact in the second person space, we need to synchronize these two users within a global coordinate system. And it's this global coordinate system that becomes the key issue. So, why is this an issue? We need to think about two things. One, spatial temporal inconsistencies. So, in the typical scenario, everything is good, no latency, no tracking errors, no registration errors, a person can interact with the virtual content. However, in the presence of any of these areas, it can be very frustrating for the user because content is not placed where it should be, and with the added latency, it makes it difficult to interact with the content. Then, when we talk about moving around larger or urban-sized areas, there are several things we need to concern ourselves with. Of course, users are more focused on the AR content, and as a result, can end up in dangerous situations. Also, we're navigating users around a large area. We need to provide them awareness of their surroundings, and also give them some information about their local area. Finally, if we have many distributed users, we need to think about how we can allow them to collaborate in an efficient and effective manner. And also consider the fact that because they're distributed, we need to worry about the networking bandwidth. Now that I've summarized both the technical and design aspects, let's start with exploring the design space to be able to allow us to create some guidelines in order to create such an experience. So I'm going to start off with the technical again. So first thing we need to look at is how do we display content to the users. And for this, I'm going to categorize three more specific and more pliable ways to display this content. The first being video see-through HD. And for this, we have a VR display, some camera showing the video feed to the users with the augmentations attached. Whilst it's easier to match the computer graphics because we're showing the video and can match the graphics to the video, there is a higher latency and can be potentially dangerous if the display fails, as the user's view of the real world is occluded. Then, we can think about handheld video see-through displays. We need to, when we take a look at the real world, we do this through a tablet interface, and therefore we use a video feed as well. This makes it, again, easier to match the CG, but has the benefit of decoupling the user's natural view of the real world from the augmented scene, because the augmented scene is attached to the tablet. Therefore, latency is not so much of an issue. The user can simply stop looking at the tablet if they feel disoriented. However, this is less immersive than a head-mounted display. Finally, we look at optical see-through HMD. Now, this allows us to augment directly into the user's environment, the computer graphics content, through means of a transparent optical system. This makes it harder to match the computer graphics because we need to emulate the eye instead of a video camera. But this has the benefit of a minimal world view latency. The user sees the real world directly. Therefore, latency is not such a big issue. It's only the computer graphics that are going to experience this problem. Finally, a failure in this case is again still okay because the user can still see the environment around them. It's no longer dangerous. Moving on, we don't really need to display content to users. We need to track them in the environment. Then, again, categorizing some means from least to most suitable. First, we can look at visual markers. Now, this is akin to a piece of paper with a QR marker being placed on a table and then some external device looking at this marker to get the pose. Now, this is low cost. You only need to print some markers out. This has high accuracy, provided the marker is visible properly to the camera. But it's limited in scale. We need to place many of these in an environment and also very carefully calibrate the in-between transforms. Moving further forward, we have outside-in tracking where we place visual markers on the user and many external sensors in the environment. This can be very difficult to calibrate many of these sensors, especially when we have them spread out over larger areas, and is limited in scale because we need to think this can be very expensive very quickly if we need to deploy many of these sensors in a large environment. However, this is a very high precision, especially if the calibration between the sensors is very nicely formed. Moving on, we can think about sensors as well. So this is akin to using the GPS and gyroscope, normally seen in a mobile phone. This is very low cost. No extra cost to the developer, no extra cost to the user because they have the device available. And it's capable of large scale as already seen in Pokemon Go. But again, as seen in Pokemon Go, this can lead to big problems in accuracy. We can also think about many research-oriented visual slant techniques. that basically estimate the user's pose in the environment through means of sensors placed on the user. This can be very highly precise, and drift is possible through larger areas, but this has the benefit of being hit large scale, just out of the box. Finally, we can think about a hybrid of these systems like ones found in the Microsoft HoloLens or the Magic Leap, which combine this visual slant tracking with onboard sensors in order to improve the overall drift over the large area. So this leads to very high accuracy and is definitely capable of large scale and is compensated from drift because of the onboard sensors. However, nothing has been developed in such a scale with such a device. And this leads me to the second thing that we need to explore. So this is all about the user interface design. Now, typically in AR research, we only focus on the UI UX specifically, but my idea is because games have been widely envisioned in augmented reality, we want to try to derive many of the UI concepts and user interface concepts from video games into augmented reality. And this is where I handle this approach for these design aspects. The first, talking about spatial and temporal inconsistencies, just to reiterate, there are two scenarios where there's no latency, and no spatial inconsistency, and when inconsistencies are present. Looking at this, we need to think about two things. First, representing the user and how to provide the interactions. Now, for representing the user, we can either use direct representation of the user or the tools in the environment. Now, this can only be applied when there's low or no spatial temporal inconsistency, but has the benefits of being natural to the user as they directly interact with the content, and very satisfying. Imagine you walk up to a garden, virtual garden, and can plant and water the garden yourself. However, as I said, it's susceptible to latency and tracking error, which can lead to many problems. Alternatively, we can think about indirect interactions with the remote avatars. Whilst this can be a bit unnatural for the user, they need to think from the avatar's perspective during interactions, and can be a bit unsatisfying because they no longer perform the interaction themselves. It is very robust to latency and tracking error. Even if there's some post-synchronization error between clients, this post-synchronization error is effectively hidden by the placement of this avatar. Moving on, again, we need to look at the interaction with the content itself. We can think of this two ways. As I said before, we can think directly. It has the same problems as visualizing the information to users as with the interaction itself. Or we can think two alternatives. The first is tagged and assisted interaction, where basically we select the target with 4 interactions and then orient whether the avatar or modify the input pose in order to perform the interaction, so that way it's always on target. Now this can be again very unnatural because the system is modifying the user's raw input, but can lead to visual consistency between clients and is robust to tracking and latency errors. Alternatively, if we're using projectiles, we can think of magnetized type interaction. The first, where basically if we fire a projectile in space, this projectile essentially acts like a homing missile moving towards the interaction target. Again, this is very unnatural. Users would normally not expect this to occur, and can be not so visually consistent with what they expect of the real world. However, it is still robust at latency and tracking errors. Moving further forward, we'll also introduce a second problem of how to move users around a large area. So, as I said, just to recap, we have several problems, the first being dangerous situations that we need to avoid, and also how to present the information to users so that they have an understanding of their environment. First, we need to look at the spatial awareness phase. Now, usually there's 2 ways to do this. Typically in AR, we focus on in-HUD heads-up display information. We have a display in front of the user, and on this display, we directly place symbols, text, and annotations for the user to view. We also can think about what's mainly done in video games of using the environment the user has around them, whether it be virtual or real, and augment this environment directly. So for example, in Far Cry, normally when the user looks at the map, the character in-game would pull up a physical representation of this map and then annotate this map directly with the information the user needs. When we think about this, the best approach is to combine both. One where the user can look at the environment and still see the cues, and also one that's more immersive when they look at the 3D environment itself. We also need to perform crowd control to avoid these situations which are dangerous. So, for example, we need repellers, something that we can associate with danger, so that we know instinctively to move away from it. Alternatively, we need some way to attract the users towards our intended targets. So, for example, we have a pretty princess asking for help. Of course, the user, feeling strong, wants to move to save the princess. This is what we would call an attractor. Now, there are several ways that we can present this kind of information to users. As highlighted by Fidelity et al., we can think of this as visual and symbolic, visual diegetic, as in part of the environment or the experience, audio, for example, alarms being played, or tactile feedback. If we have a hand controller or some vibration motion, we can give users this response by vibrating the specific device. We can also look at, from the distributed communication side, just to reiterate what this problem is, we have many users around a large area, we need a means to effectively communicate this, and also consider the latency and bandwidth problems. So just like with displays and the tracking, I'm going to list several options. First, the communication itself. We can think of this in three ways. With low bandwidth, we can think of text input. This is directly, user types in text and sends a message, and the other users can read this. This is very low bandwidth, very clear, but it requires a high cognitive load because users have to spend time to read this text, and requires either a physical keyboard or some means of virtual input to provide this message. Alternatively, we can think of single message emoticon systems, like for those used in games. More recently, Fallout 76 introduced a concept where instead of talking to the users or using text, instead they can bring up a radial menu, select a tagged action, and the character will perform this action for other users around them to take a look. This is very low in bandwidth. It has the same requirements as text messaging and has low cognitive load. However, this can be ambiguous. It's not very clear sometimes what this emoticon is meaning, and is limited to the amount of actions that are pre-programmed. Finally, if we have a high bandwidth, we can just directly use voice. It's more natural and also clear instruction depending on the person speaking. However, this requires high bandwidth and is also again limited to the range of actions, as users can talk about objects that are visually appear to one without being visually present to another. Now that I've described the basic design concepts behind creating a large-scale high-fidelity system, I want to now talk about how I've created this large-scale high-fidelity system based on these designs. I'm going to talk about first the technical aspect. And quite simply, first looking at the hardware, we talked about displays and tracking. Well, the HoloLens already has visual SLAM and combined sensor tracking, and uses an optical see-through setup, allowing users to directly see content. So it's natural we pick the HoloLens. An alternative is the Magic Leap, but it wasn't available at the time of development, so I went for the former instead of the latter. And for input, I just used an Xbox 360 controller rather than the inbuilt interactions the HoloLens is capable of. Then the software workflow is as follows. First, a user scans several small areas around there, that's about the surrounding area, then uploads these smaller 5x5 meter areas to a cloud system. Then this cloud system will perform an alignment for each of these smaller maps to create one global scale. You can see in this picture, this is a reconstruction of the NICE campus, including all of the buildings here, also including the Shockador, so 230 meters by 230 meters. Finally, by tracking a user relative to a local map that's loaded, and then synchronizing the transformation of this local map to the global coordinate system, and distributing this global coordinate system overall, we can track and place content in the user's environment. Why do we do this, though, when the HoloLens is already capable of large scale? This is because, as we can see here, the HoloLens itself has some drift associated with it, especially when synchronizing multiple systems. So for a quick test to verify that my system helps, I've created this alignment, as you've seen in the previous slide, then placed two HoloLenses in this environment, tracking both against the HoloLens itself, and using my system, which contains the global coordinate system created by our alignment. Then we orient the HoloLenses towards each other and slowly move them away. While slowly moving them away, we take several pictures, augmenting a scene with both a blue crosshair for the native HoloLens system and a red crosshair for my system. Then, for my system, we can see as the HoloLens moves further away, especially at 75 meters, my system doesn't perfectly account for this accuracy, but still is a massive improvement visually compared to the input native HoloLens system. Using this system we've developed, I designed and created the first instance of a large-scale high-fidelity collaborative AR game, also known as HoloRoyale. The basic point of HoloRoyale is many users, in this case Dot On Body, walk around with several HoloLenses and defend Dot On Body against these virtual robots, which are scattered around the entire area. Now this incorporates many of the design aspects which I will discuss in a few later slides in order to do this. And as I said before, this system is done by quickly first creating a map by scanning several areas of the environment and aligning these several maps in order to create the one global coordinate system. But although we've created this system, we need to apply the design space to hide the problems the system has. It's still not 100% accurate. So by creating this game, we applied the concepts found in our design space. The first of this is representing the users and interacting with the content. As I discussed earlier, because my system isn't 100% accurate and is distributed, it's likely that users are going to have some spatial temporal inconsistencies presented to them. So because of this, as we can see in figure A, a person, one of the professors in this room, is walking around Dot On Body and is being followed by two virtual drones. These virtual drones represent this particular person in our AR environment. Then, if this person goes to shoot a virtual robot placed in the scene, although that they hit the target from a third perspective without any compensation, we would end up seeing a miss from a third perspective. This is where our assisted aiming described earlier comes into play. By tagging and orienting our virtual avatars towards the target of interaction, we can provide this consistent experience to everyone. Then also discussing fitting the game design to the design space suggested, we created the following UI that contains first attractors in the compass bar. Now this compass bar basically places content about key locations relative to the user's location and orientation. Additionally, we provide some spatial information and attractors in a world miniature at the bottom of this display. And from this we have three variations as shown in B, C, and D. B, a full 3D model that's been simplified of the environment. C, a more simplified version of that world in miniature, which just shows overlays of the walls. And D, the raw positioning and relative positioning of the user in the environment. We also provide diegetic repellers for keeping users away from their environment. So this is the roadwork sign that we can associate with "we should not pass here." And additionally, as an addition for moving and navigating the scene, we provide symbolic navigation guides. Finally, although you can't hear the communication, we provide this information on screen to the users. So if a user is talking, that user will be present on the left-hand side, and through single message text emoticons, they can send instant text messages to each of the users if the voice communication isn't enough. I demonstrated this demo in two places last year, the first being in Berlin, Germany, and the second in Munich. And the basic idea was we had several people come and play this game at the conferences and just gives us some general feedback about the entire experience. What we found was that many of the people who played this game respected the virtual repellers, even though we know that the virtual repeller has no physical effect on them, and there was nothing telling them not to avoid it. Moving a bit further forward, we decided to explore this more deeply because, unfortunately, these conferences were limited in scale, and we wanted to see what this environment would be like should we have a larger scale. For this, I designed a user study by deploying HoloRoyale on the NICE campus, and then creating 4 set targets for players to move to. The idea was that we variate whether the repellers are visually appearing or whether they weren't present, and then comparing what happens in the two scenarios. This has 3 parts to this experiment. The first, users scatter in groups of 3 to defend the target areas placed in the environment. So they end up scattering to separate areas. Then they defend these bases for a period of time. This allowed us to set up everything for the second part. So what you can see on screen is this first part of one of the three people at one of the three locations in the experiment defending the area. Then, once the area was defended, the second part begins, and one of these four targets appears somewhere on the campus. Users then had to navigate themselves towards this target and stand at this target for a specific time. Then, during this, as you saw in the video, we had two conditions, with and without the repellers. If the repellers were present, we wanted to see if users directed themselves around. The hypothesis, of course, was, one, participants will respect the barriers formed by these diegetic repellers. And then two, the virtual diegetic repellers won't significantly impact the participants' enjoyment. And we say this because our hypothesis states that although this information is being placed in the user's environment, it's part of the user's environment and is less disruptive as a result. So, during the experiment, we recorded the poses of these users and plotted them in a heat map. Now, these red highlights show us that directly there is a big change between when repellers are absent and when they're present. We can see, especially in target B's case, when we set up a blocked off corridorway, using our repellers, users no longer walked down that corridorway. We also created 4 different scenarios, not specific for target placement, but to try to emulate the kind of situations. Target A looked at navigation around a large area. Target P looked at the corridorways, whether they're being blocked off. Target C looked at navigation in a smaller room-sized area. And then target D, we wanted to try to provoke this last-minute response of users when they saw the repeller. Then, looking at the next slide, we also performed a questionnaire after each session with the repellers and non-repellers present, and they collect this information back. And to quickly summarize, this supports statistically that the virtual repellers don't affect the user's enjoyment of the overall game. However, what we weren't expecting and what is being shown was that the repeller significantly impacted the ability to perform actions of the users, their mental image of the environment, and whether they could communicate well with their partners. And this can be simply explained for question 3 about performing actions, that the repellers prevented them from walking into an area they wanted to. So it's very self-explanatory. Question 4 shows us if the user had a good mental image, and we can explain this that the repellers added some confusion to the environment, making it harder to understand. And then finally, question 5, we followed up after the experiment and asked some questions and found out that basically the participants had some difficulty trying to present what their intentions were when regards to the repellers. And this is related to, because one user can see the repellent, the others cannot, it's harder to describe where it is. However, this user study has some limitations. One, I only focused on one type of repeller. Then, additionally, I only focused on the look of repellers because this was the most interesting thing we found out during the demonstrations. This is the topic that I focused on. Finally, I also noted that the environment doesn't match our target scenario. The nice campus was intentionally very empty, and additionally, for participant safety, each participant in the experiment when playing the game was shadowed by a non-speaking person in order to prevent some safety issues. Normally, we wouldn't want a person overlooking a player in the game. We would want these attractors and repellers to perform well by themselves. For future work, I need to look at the applicability, the threshold of whether users start noticing these spatial temporal inconsistencies, the psychological effect of repellers and attractors, particularly if they're very dangerous visualizations, like, for example, a fire enveloping around a user. And finally, what is the effectiveness of this indirect assistance? Moving on, I want to talk a little bit, although not so detailed, it's still very important, the second part of my thesis, which evaluates the fidelity of refocusable content on an optical see-through HMD. And just to give you a brief introduction and recap of my master thesis, and to show you, first, I used the HoloLens for the first part. This, however, has an innate limitation that it doesn't model the user's eye. This means that for typical optical see-through HMDs, when we display content and the user is looking at an environment, the natural view of the environment will experience defocus, but the optical see-through HMD will always be in focus. This is where the system in my master's comes in by recreating this focusable content and displaying it on the HMD. It did this by using an autorefractometer to measure the user's eye, and then ray trace the depth of field artifacts that we normally experience and displaying this to the users. So just to recap the related work, there are several types of ways we can show this kind of refocusable content. The first with multiple focus planes, where we have multiple focal planes that we can display content on. The second are refocusable lenses, which has a lens that manually refocuses for the user in order to display this refocusable CG. Finally, we have also matching camera parameters, and this is actually the related work that's most closest to my work because they model the visual lens, the lens system of the camera, which they create the augmentations, whereas in my case, I end up using the user's eye measurements. Additionally, this part of my thesis was about evaluating the effectiveness of such content, and for this, I needed to look into Turing tests for AR. Now, what is a Turing test? Basic concept: a guy named Alan Turing put a user in front of a computer and a user interacted with the computer with the intention of guessing whether this interaction on the other side was performed by a computer or by a real person. And the aim was to try to discern whether it was real or a real person or a computer interacting. This has also been done in computer vision. Users have been shown a reconstruction done by some computer vision technique and comparing it to the real environment. The user had to guess which one was real. Then, moving on, of course, in computer graphics, this is always done. But more recently, NVIDIA showcased a box enclosure, which they showed two things. One, a rendered drill using ray tracing, and a real drill with the same lighting environment. Then people in this demonstration would take a look at this and try to guess which one was the real one. My experiment aims to follow this kind of idea, to try to allow the users to refocus along a real scene and try to discern which of the three pillars presented to them was in fact a virtual pillar. And for this we had three conditions. We had either a real pillar, all three of these pillars are real, with one of them being fake. Then, for the fake pillar, whether the autorefractometer measuring the eye was on and therefore recreating this refocusable content, or whether this autorefractometer was off, having a normal, typical optical see-through HMD setup. So, this experiment's hypothesis, with the autorefractometer off, participants would guess the virtual pillar more correctly than if the autorefractometer was on and the virtual content exhibited this refocusable simulation. Then, second, with the autorefractometer on, participants will only correctly guess the virtual pillar no better than random chance. During each session, we would show the user the scene. They would then walk away on a separate area, try to guess which one of the three pillars they saw was the fake pillar, and then repeat this several times. From this, we had 12 participants, and we had the following variables. We variated which of the pillars was virtually rendered, red, green, or blue, whether the autorefractometer was on or off, and the trial sequence that occurs. From this, we first did some preliminary tasks before the experiment in order to make sure the users can actually perform. First was an eye dominance test to make sure we understood which eye was dominant, because the autorefractometer only measures one eye. In this, the user simply places their hands and then circles a target, and then naturally what ends up happening is this circulation ends up being over their dominant eye. Then we did a typical optometry acuity test in order to make sure the user's eyesight was good enough. Finally, we did an operability test in order to ensure that their eye could be measured by the autorefractometer. For example, many Asian eyes are very small and the opening is not so large. Therefore, it's quite hard for the autorefractometer to accurately measure this. So this was just a quick study test to make sure we could use it. Then, as I said before, the user sat down at a box enclosure with us set up inside it, emulating an optical see-through HMD. We placed the three pillars, one after the other, and then evaluated whether the autorefractometer was on or which of the pillars were virtual. The results, although the first hypothesis passes, users were less likely to guess the real pillar the virtual pillar, when the virtual pillar was present. Unfortunately, for all three pillars, we weren't able to achieve this as random chance. We could only achieve this for the blue pillar. And I'll quickly explain why. This is an inherent limitation to this system. Because our display is fixed at a single focal length, then when the user is looking at distances differ from the focal length of this display, the content can never be appeared sharp. So for example, in the above image, I showed a red pillar, which is virtual, and two scenarios, whether they're virtual or real. We can see in the real image, when we focus on the back pillar, the red pillar, it's in perfect focus. However, because of this screen depth disparity, unfortunately, we can't render this content sharply. Even though our rendering on screen appears sharp, the user's view of that display appears blurred. And this is where the future work comes in. This is from two parts. One, solving this screen depth disparity. One of the things investigated in my thesis was trying to correct this screen depth disparity. And then additionally, to try to integrate this in an optical see-through H&D. My system was still a tabletop type prototype, but it's always more natural if we can integrate this into a typical optical see-through H&D setup. As you can see here, we've done a variation of IAR, which just uses a raycast from the user's view of the world in order to determine where in the scene they're looking and therefore what part we should be blurring. These are the publications achieved. Now, I'm only listing the publications achieved during my PhD thesis, and omitting the ones, although they're on the same topic, performed during the master thesis. And to summarize, I explained in two parts. The first being about this creation of a large-scale high-fidelity system, and the second part, evaluating the refocusable content and optical see-through system. I made the following contributions. The work at first to explore this unique domain. The work establishes the design space in this domain. Then the system created in this thesis improves the accuracy of synchronized poses between multiple science systems. Then, of course, I showed the first instance of a large-scale high-fidelity collaborative AR experience. Finally, during the two experiments, I first showed that virtual repellers are effective means of crowd control. And then for the second experiment, I showed that for optical see-through AR, rendering refocusable CG improves the fidelity. Thank you very much for listening, and I will be happy to have some comments.
Okay, so now let's ask some questions. Christian, can you hear me?
Hey Chris, are you there?
Yes, I can.
I want to get a question first from the audience, and then give a chance to Kyoka-sensei, and then I'd like to ask you some questions. It's okay?
Sounds good.
Okay, for some questions from audience. No question? No? Okay, later. Okay. Kyoka-sensei.
Yeah, good.
Thank you very much for the presentation. It's amazing. So you tackle many different problems which you realize the large-scale high-fidelity collaborative system. But at the same time, you tackle many different things, and then the solution, some of the solution, they sounded, very advanced, and some of them actually did not. Some of them, the solution itself, trying to solve the particular problem that is new is already a challenge, I know. But the solution itself, like the visualization of the indirect signs, symbols on the normal display, sound like trivial.
Right.
So can you explain your proposed techniques in order of your contribution?
So,
or novelty?
So the first part, I'm technically deriving a lot of the suggested proposed fixes from video game design concepts. Normally what happens in a large video game, many of the server-side systems perform this indirect interaction, modification of input, and also the visual output. Now, in theory, this sounds very simple, but just because the idea is simple doesn't mean it can be very powerful when applied to the right place. And this is ideally where my contribution lies, the very deep thought that says that, hey, we can derive this from a game because we can experience this in games, therefore it's very applicable to the augmented reality space. So, to summarize, yes, some of the ideas may be simple, but that doesn't excuse them from being very novel, or the application of those ideas being very novel, giving us a superior results. It's true, technically we hide the problem in the first place, but unfortunately that can be the nature of some systems in order to provide a consistent experience.
Yeah, I understand completely. So nobody has shown proven, that kind of technique will work in a large-scale IVR system, because there's no such system like that. But maybe you want to sell the solutions more than the others. So what do you think are the most, the most selling?
So from a research perspective, the biggest impact is actually this design space that was explored. So in this slide here, this single summary, the single image, is one of the biggest contributions of this thesis because it gives a very precise guideline based on previous design methods and how this should be implemented. One of the other big impacts is this technical implementation, but this is a research contribution altogether, therefore it's a bit weaker.
This table looks like very inspiring. We will stimulate much more further follow studies. So I think it's very cool. Okay, so I would slightly change the wording of the question. So what was the most technically challenging?
The most technically challenging, of course, was creating this large-scale system. Just simply speaking, synchronizing several users over the large areas is already a big technical challenge, and was the majority of my thesis' time developing.
For example, they're using the smart technique to split the entire scene into many different groups. They combine them, and that describe very briefly in a presentation, for example.
So yes, this is described very briefly, and the actual system details itself is very detailed explained in the thesis, but because this isn't a research contribution, I kept this part of the presentation brief as a result. But from a naive viewpoint, hopefully from this presentation you can understand how I've approached this problem.
Yeah, for example, about alignment. So you show the user's views. And you showed some research and errors with algebra technique, but you didn't show the original raw the constructed.
So just to be clear, you're saying that I don't talk in specific on how the reconstruction is performed?
No. You describe the technique itself, but you can compare the shapes of the reconstructed scene without.
Right, I don't actually verify that our alignment is actually better. That's not the target of this thesis. The whole target of this thesis was saying that if multiple slant systems inherently have drift, that means over larger distances, the accuracy of the place content, what we see, is much worse. My aim is not to fix the visual slant system, but rather to hide the system's problems by using a third party to create this global coordinate system. This is what allows, although technically I've modified 0 with the tracking algorithm, but by bypassing it in a sense, I'm able to create this much better augmented scene.
So, for example, you still show the direct overlays, like the roadwork sign.
Right.
So that means that you still rely on some level of accuracy.
Right. For example, if this alignment is very bad, then the result is going to be very bad. It's only under the assumption that alignment is better than the device itself. Does this work?
So what do you say when and how you combine it, you use indirect overlays in addition to the direct overlays?
So,
or maybe when you don't want to use the overlay, direct overlays.
So you're basically asking when do we use my suggested direct interaction and visual representation?
Is your suggestion always combine, always show the both direct and indirect overlays?
So, I mean, we can think of it that way. We can think of it as a dynamic system that can detect whether everything's accurate and therefore we do everything directly, or we can do everything indirectly when it's not accurate. But for this specific thesis, I dictated that the first, if it's very accurate, of course it's much better if we use direct representations, direct interactions. However, in the presence of visual, spatial, and temporal inconsistencies, the indirect representation and the indirect interactions should be used. Now, we don't actually know what the thresholds are for this kind of detection for these visual inconsistencies, which is why in the future work, I've suggested that we investigate this further. In fact, one of my next studies is aiming to perform a series of interactions with users in order to see what point do we experience uncomfortableness during this interaction under the spatial temporal inconsistencies.
So the usually covered the several websites, paper. But did you already submit this first part to St. John?
Yes, I've submitted to computer and graphics. It's still under review. My hope was that we would get the result very soon, but we are still waiting. So basically, we will know within the next month, hopefully, if this has been accepted, rejected, or is under some revision.
I see. So the I still see some gap between the first and second part, and I think probably you will have some difficulty comment and smoothly. But in that sense, I think when it comes to the long scale AR, the depth of the development of the depth of field will be larger, because you will see some short things like the yoga, or maybe something animated very far. So did you have any actual problem of the depth of field
Now,
in the large scale?
in the first instance, we didn't specifically test this. So, specifically speaking, the user interface presented was placed at the same distance as the virtual content they look at, or the real-world content, and we don't emulate any depth of field stuff in the first part. But, of course...
I was hoping to make some glue.
Yes.
Extract some episode or something, even though it's chronological opposite. But
so this is where the future work of the second part comes in. Although we created a very naive version of IAR, it's still much better if we had the user's information and integrate this in an optical see-through system.
But still, maybe you can add some lines that connect the two parts. So in the first part, it would be nicer to have a display that's capable of the view. And in the second part, maybe you can also write this to be used in the AO system. We're ones like in the last system.
Okay. Thanks for the suggestion.
Thank you. Christian?
Hello.
Hello. Yeah, as I am the fourth supervisor of these theses, I would suggest first that the other supervisors ask their questions and I go last.
Okay.
Just Kyoka Sensei gave a lot of advices. So it's your turn.
Chris? You there?
I'm there.
Yeah, so a couple of senseis asked if you could provide your comments now, so that way we can, because of course you're the one that worked the closest with me and therefore would have probably the most impactful suggestions. So it's better that you, because it may be very long, you might give your comments now if that's okay.
No, I would really like Kato Sensei and Alex to go first.
Okay, fair enough. Alex?
I have a question about these. Have you proofread it?
I have, but as we all know, my proofreading is not the best. So likely some things have been left through.
Yes.
Yes, I mean, when I went for this news, it was very clear that it was largely copy-pasted with still mistakes and missing figures, and the figures appearing at the end of the chapter, which makes it a bit horrible.
This is actually a result of the template. The template forces these figures, if they fit on the page, to be put at the end.
But you can surely somehow modify it so that they appear close to the way referring to them, or change the size of the figures if necessary. I mean, my main points were along the lines of kilocalories, as you know, that the first part and the second part don't seem very strongly connected.
Yes. Well, to be perfectly transparent, they are two very different subjects that I investigated. The second part I investigated at the start of this thesis, but then decided to work on a new topic. Although it's along the same lines of Fidelity, on paper, they seem very different from each other.
Now, according to this, your second experiment had absolutely no limitations.
Wrong. Of course there are several limitations. One, we had a box enclosure. This is already listed in the thesis, is it not?
There are some limitations listed in the discussion section, but they are not really outlined as a separate paragraph or a separate section that should be done.
Okay, so you're asking me now to, in the thesis, separate the limitations in some section. Okay.
To add the limitation section that discusses what are the limitations of your previous work. Right, so I think you described very, very nicely in your presentation, much better actually than in the paper, why you created the different pathways. Now, was there any interesting observation you made? Because this is not coming out in the thesis at all.
Well, in the thesis, I actually list that under one of the situations, particularly in the last second. So let me bring up the slide that shows the different layouts in order to visualize the things I'm about to say. So more specifically, for target D, at the last second when people were approaching, the alternative pathway meant that they had to backtrack significantly in order to reach the target. Now, in one or two of these trials, and out of the total, one of the users was almost verbally harassed by their teammates to just walk through the barrier and ignore the game's rules in order to get the target more efficiently. So, of course, during the experiment, one of the limitations was, although I didn't say it today, was that I provided no visual reinforcement of these repellers, and it's actually listed as future work. So this was one of the few things that I observed, which was quite interesting during the experiment.
So, what would be your advice for somebody who is aiming to replicate something similar to you, but is, let's say, targeting a different application scenario?
You're getting a bit general here, but just to make the question a bit clearer, say I'm going to make some gardening scenario, Minecraft, for example, like a large-scale Minecraft system, then I would suggest in order for users to experience this system very nicely, first, of course, we need these visual repellers in order to prevent users from inadvertently moving into a dangerous situation, dangerous area. And as I suggested earlier, the system needs to be able to detect if there is some spatial inconsistency or visual latency when interacting with the content, and then adjust what's shown to the users appropriately.
Yeah, I think that the series would definitely benefit if you had, let's say, some other section or chapter that is outlining different scenarios and how your design space plays into these scenarios. As a hypothetical, for example, we are reading the 3DI book.
Right.
And in there, they're describing how they design this particular scenario based on different considerations.
Would this be similar to my discussion section in part 1 of my thesis, where I briefly overstate that we need to look into how this design space can be applied?
Yes, and I think you should probably make some examples where you specifically say, okay, there is scenario one, this is how I apply this design space. Scenario two, this is, let's say, it's developed on a mobile phone, this is how I'm going to apply this design space.
Okay.
So such examples would make them much, much nicer read in the long term.
Okay, thanks. Is that it?
And I think you're missing somebody in your acknowledgements.
I need to double check that.
I'd also want you to describe some future technology versions or future technology improvement, and that will even expand the framework or some the overlap directions. So, for example, the software that your system really depends on the HoloLens.
Mm-hmm.
But for example, the standalone technology display, more standalone technologies are coming out.
Mm-hmm.
And for example, I had some kind of development FPGA-based video system technology display that it has a very suitable latency, and then you will have much more the wider preview. And so you probably don't have to exclude them all.
But it's still, at the end of the day, a video see-through head-mounted display. The second the system fails and turns off, a user is blind to the world around them, which is the reason, one of the other reasons I say that this is ill-advised, especially if we're walking in a very crowded area. It's become super dangerous. That's the main reason one of the main reasons I highlight why a video see-through display is super unsuitable for this large-scale urban environment.
Maybe. So my point, just 4 years ago, there was nobody in the factory except the people inside Microsoft dreamed of that kind of standalone, high accuracy, standalone display. So maybe in the discussion section, in the very last part of your presentation,
Okay.
you may be able to add some more in the future direction.
Okay.
Which could change or expand your learning.
Okay, that's possible. Thanks for the comment.
Yeah, some question.
Your turn. I have to answer.
The last night you had answers. Okay, I have three questions. Number one, so when we look at I read the AR textbook, AR technology can be divided into three categories. One is geometrical consistency.
Yes.
One is temporal consistency. One
Yes.
is the photometrical consistency.
Right.
So mainly you are focused on geometry and temporal consistency. But
Right.
you didn't mention about the photometrical part of the technology. For example, so I'm not gamer, so I don't know the game itself, but sometimes the game needs high quality 3D graphics.
Right.
Maybe it's same in the AR situation. But
Right.
when I look at your demonstration, you don't focus on the reality rendering of the 3D content.
This is
But
true.
sometimes this kind of the high quality 3D graphics will be required. So when you define the fidelity, maybe one of the aspects of the high fidelity includes the photometrical quality of the contents. Right?
So, although I didn't use the same keywords as you, and probably my thesis doesn't reflect this strongly enough, that this is a problem that does exist but isn't largely explored. But visual consistency is the term that I use to explain this kind of photometric consistency that you were talking about, or this quality, visual quality of the AR scene. Yes, this is a problem.
Yeah, actually, in the AR scenario, in order to improve the photometrical consistency, estimating the lighting condition is also an important part. So you don't need to show the solution of that one, but in the introduction part, it's better for you to describe this kind of issues.
Okay.
This is number one. Number two is tracking. So you already mentioned about tracking, but when we think about the tracking, it also can be divided into two parts. One is the head tracking based on the world coordinates. Another tracking is the object tracking. So mainly HoloLens provides us head tracking. So we can get the head pose and position based on the world coordinates. But sometimes object tracking sometimes can be used in the game. So also you should mention about this importance of the object tracking. So I don't know, maybe if you want to, I don't know, but some game probably they require object tracking, not head tracking.
Right. So, for example, just to clarify, you're talking about if we're looking at the tool for the user sees and interacts the environment with.
For actually this case, if we have some gun, I want to render the beam from the top of the gun.
Right.
In this case, we need to track the position of gun.
Yes.
Right? This kind of object tracking.
Yes. So I actually described this very nicely in my thesis, but also in the presentation, that the concepts described in the presentation and the thesis are equally applicable to the object tracking or the objects in the user uses for this interaction, as well as the head pose. So this is ambiguous to whether it's the user's head pose that we need to hide under spatial temporal inconsistencies or
But just
the head pose.
as they mentioned, so currently your system rely on the HoloLens technology, but in future, maybe 10 years later, probably, I hope we can use very nice object tracking system with some head-mounted displays.
So interesting you say this because just after I developed the system, the Magic Leap came out and it includes a hand track controller. But interestingly enough, the hand tracking is very bad and very inaccurate.
Yeah, now it's bad, but in future, maybe not only the hand tracking, but some human tracking and some object tracking, if it can be available, it will be available, maybe design concept will be changed.
Okay. Okay, so can you just note
But
in my thesis?
that's maybe just a future something.
Okay, so just add that discussion in my future work. Okay, yeah.
And then number 3, user interface. I don't know if this is good. Because your system, you propose to use a standard game interface. But some gamer, like not a standard game user interface, but when you enjoy the Formula 1 game, they use some handle or some special user interface. Some people use some shooting gun or something like that. Why do you choose the standard game?
This eliminates any, how can I say this? This basically eliminates any external factors into the interactions of our system. So rather than relying on some specialized controller like a gun or some visual hand gestures, we give already a standard in video games, this Xbox controller, but it could have been any gamepad because it's already a standard in the video game industry and it's less of a variable, especially in our experiments.
But so the main important part of this thesis is fidelity. I don't know the exact definition of fidelity, but user interface is one of the aspects of fidelity. High fidelity user interface and low fidelity user interface. In this case, just standard gamepad is high fidelity.
If the gamepad itself, we can consider not high fidelity, but because we don't visually use input from the gamepad, it's only merely we activate the gamepad and then the visual input is triggered into our system. We can consider it from this perspective as high fidelity, although the gamepad is separated from the visual content, it's got nothing to do with the visual content.
So what I want to say is the most important keyword of your thesis is the fidelity. So discussion about fidelity is very interesting part of your thesis. So if you add several types of fidelity, it's improved your thesis. So my first question is about the fidelity of photometric consistency. Second part is the fidelity of tracking. The third, my question is the fidelity of user interface. You don't need to solve the solution, but just clarify what kind of fidelity is this in game design areas.
can we discuss this a little bit later? Because I may very well have covered what you've asked, but with very poor wording, and I need to just verify that this is the case, or if I have missed this point.
Okay.
Okay.
I'm sorry, it's almost time, but how long do you need?
Depends how long Damien needs to answer. Damien, can you show your contributions, please?
Sure. Okay.
So my first question is, so number 3 says, right, your system improves the accuracy. Normally when you say improve, then it's compared to something. So compared to what does it improve the accuracy?
So, okay, 2 things. One, this text is quite bad. I should clarify that this is the visual accuracy of the system. 2, the comparison is quite simply the result of the alignment using my system for synchronizing closes versus the direct raw input from the HoloLens's SLAM system.
But the sentence is about multiple SLAM systems.
Right. So in this case, it's... Sorry, continue.
So this sentence is about multiple SLAM systems.
Right.
Now, what are the 2 alternatives? I mean, what is the standard way to synchronize multiple SLAM systems versus your way?
The standard way is just using the direct raw pose from the internal SLAM systems map. So we have 2 devices that walk around in a particular area and do a map of the environment of that area, and then we directly synchronize the resulting poses from each device's own internal map.
Okay. Yeah, I think in general the contributions should be iterated and refined, because there's some, I don't know, it's basically hard to understand what number 3 says. Mm-hmm. Also, what is the question between, what is the difference between contribution 1 and contribution 4?
So we just read this quickly. The difference is that number 1 talks about the design space and design guidelines. Number 4 shows the first implementation using this design space, therefore showing how we can apply this design space to such a real world scenario.
So number 4 is that you created a prototype. Right? This is what number 4 says.
Number 4 is about creating the experience, not the prototype. Number 4 is all about how to apply the design space to create an experience.
But isn't the design space contribution number 2?
Technically, you can think about the design space in 2 parts. One, the mere fact that I've taken the first step into this domain itself is a contribution, but number 2 and 4 about what I did during the first step in this domain. So number 2 talks specifically about the deriving of this design space, whereas number 4 talks specifically about the experience that can be created from this design space and how we can apply this design space.
Okay, so this means that 2 and 4 should maybe sub-points of 1. Right, because 2 and 4 are your means for doing 1.
You can think of it this way, yes.
Yeah, I think it would make it more clear.
Okay.
If you show it like that.
Okay.
All right, that's it.
Thank you, Christian. Any other question? If you have short question, I can. No? No? Okay.
Feel free to approach me later if you have more questions.
So we have already 10 minutes.
Okay.
Behind, so I'd like to close this defense.
Mm-hmm.
Thank you very much.
Thank you very much, everyone.